So this starts the application 2 session. I guess to ask questions, use your virtual hand or the chat. And our first speaker is Ben McDonald from Hewlett-Packard Enterprise.
Yep, thank you, Andy. Yeah, and like Andy mentioned, my name is Ben McDonald, and I work at HPE on the Chapel team. And I mainly work on performance and user applications. And more recently, I've been working on Mason, which is Chapel's package manager. And so today I'm going to talk about an effort of implementing and optimizing Parquet IO in Chapel. So, yeah. Oops. Okay. So before I get into the specifics of this talk, I thought it would make sense to start with a quick summary of ARKOUDA. And so what ARKOUDA is a Python library that supports a key subset of the NumPy and Pandas interfaces for data science. And how ARKOUDA is set up is there's a Python client that the user will interact with and a Chapel server in the backend that's providing the scalability and performance. And that design kind of allows you to use it in Python just like you would a regular Python package. It just feel like NumPy, but you're actually running Chapel code in the back behind the scenes there. And so kind of the goal of ARKOUDA is to allow computing massive scale results within the human thought loop. And yeah, so that's kind of just a term that is just like, yeah, thought of as seconds to a few minutes. Like when you run your operation or make your request to the server, you don't want to totally have forgotten what it is that you requested from the server. And so ARKOUDA is an open source application hosted on GitHub. And if you're curious and you want to learn more, you can see that on GitHub at this link here. And so the way a typical workflow in ARKOUDA might work today is you would read in hundreds of files containing terabytes of data, and then you would perform some typical data science analysis on that data, just like you would with NumPy and Pandas. So doing operations like a sort or a group by or set operations, just any of those typical data science operations. And then finally, you could write those results out to a file. And that's just kind of a typical use case of ARKOUDA. And so since the inception of ARKOUDA, HDF5 has been the only supported file format. And the reason HDF5 was chosen for ARKOUDA is because HDF5 is kind of viewed as a standard HPC file format by many. And HDF5 was also designed specifically for HPC use. And so given ARKOUDA's goal of utilizing supercomputers and HPC in Python, like with the Python client, HDF5 just seemed like a natural fit. And so just to take a step back and take a look at what it would look like to actually be using ARKOUDA. So here on the screen, we've got a picture of a Jupyter Labs notebook where you would typically run your data science like NumPy or Pandas calls, except with, in this case, you're running an ARKOUDA server and you're connected to that ARKOUDA server. And then once you're connected to that ARKOUDA server, your calls into ARKOUDA will look just like NumPy and Pandas to an ARKOUDA user. So that user will interact with ARKOUDA just like they would NumPy and Pandas, except what's actually going on is once an ARKOUDA command is executed, it's actually sending that command to the ARKOUDA server, which is written in Chapel. And that ARKOUDA server could be ran anywhere from a laptop to a supercomputer. And then on your client code, you would connect to that supercomputer. So in that way, you can run on your on your laptop, you can be making commands and running code on a supercomputer and then getting valuable results like human readable results sent back to your laptop. And so the actual communication that goes on between the client and the server is typically not data transfer, although that is possible. How it would typically work is in the client, you would just make a request, like say you wanted to read a file, then the ARKOUDA client would send just a message as a string to the ARKOUDA server, telling the server to go read this file. And then in that way, the server is the one that's actually storing the data, executing the read of the file, and so yeah, just doing all of that work. And then once the file has been read in and the ARKOUDA arrays have been created, the ARKOUDA server will send back just a simple string to the client side, just indicating that the result was complete, and it might contain some information that would be useful to a user, such as seeing the first few elements of that array, for example. And so that's that's how the Arkuda client server model is set up. And so now getting into some of the topics more specific to this talk, here's Apache Parquet. And what Apache Parquet is a widely used columnar file format for data analytics. And what columnar file format is you can be seen in this little picture here. So imagine you have this file that has 3 columns and 4 rows. And so in data science, a typical operation is to read a column at a time, like just to read individual columns, not necessarily the whole file or just rows, for example. And so looking at how the row storage model works, and this is typical of something like the CSV file format and HDF5, it will store in this row storage format. And so if you're trying to query just column 1, for example, then you'll see your memory accesses are going to have an offset, and they're not just going to be a single contiguous chunk in memory. So you're not going to be getting the best performance there. You're going to have a little bit fragmented memory access. Whereas in columnar storage, all of the elements from each column are stored contiguously. So if you're reading a single column, that's just one contiguous chunk from memory, and that allows kind of the optimum performance for just reading a single column at a time. And that's how Apache Parquet is set up with the columnar storage. And so in this specific effort that I'm talking about in this presentation is the goal to add support for Apache Parquet in ARKOUDA. And this goal was motivated just by some increasing demand for Parquet from the ARKOUDA user community. HDF5 was no longer serving all of the needs, I suppose. So the idea to implement Apache Parquet just kept coming up. So that's what led us to wanting to implement that in ARKOUDA. And then one other goal that we had in this effort was to come within 2.5 times the performance of ARKOUDA'S HDF5 implementation. And that 2.5 times the HDF5 implementation performance was a little bit arbitrary. It was just something set by external users that wanted their functionality to just kind of fit with that ARKOUDA model I mentioned on the last slide, where you don't want to try to read in your files and then have it take so long you totally forgot what you were doing when you came back. So that 2.5x number was just kind of where that threshold seemed to lie based on the HDF5 performance. Yeah, so that's kind of what this effort entails. And so now looking at what it took to actually support Parquet and CHIUW here. So our initial implementation, it just seemed very clear to approach the Parquet C API, given CHIUW's C interoperability features. But as you can see in this little graph here and this performance chart here, the performance of HDF5 was much higher than the initial C implementation here. And if you take a look at this graph, it's a performance graph, so higher is better. And you'll notice that the C implementation isn't quite showing up on this graph because it was performing so much worse, almost 500 times worse than HDF5 with this initial implementation. So that 480x below the HDF5, that was well below our 2.5x goal that we had set for Parquet IO performance. And so there was a number of reasons for that, but I think one of the biggest reasons there was that the C implementation was not actually fully featured. So we kind of had limited room for optimizations. There wasn't a ton we could do on our end for that. And so there was limited metadata access, and it also required to read directly into arrow structures. We couldn't read directly into a chapel array buffer. And just one example of that limited metadata access. So there was no way to actually query the number of rows from the metadata using the C API. So with chapels, the way we were trying to fit this into CHIUW, we first had to read the entire file once, get the number of rows in that file, and then go back to chapel and create our chapel array based on that number of rows, and then go back and read the file again and store the data. So every single file that we wanted to read essentially had to be read twice there. So that's just a couple of reasons why the C implementation was so poor. Yeah, and so just these API limitations and the very poor performance we saw there, that led us to explore using the C++ implementation rather than the C implementation. And so for our transition to the C++ library, the reason that we chose to look into the C++ is the C++ library is kind of the standard and most feature complete library for Parquet. It's the one recommended on the official Parquet website. But of course, one of the problems with interoperating with C++ is CHIUW does not actually support interoperability with C++. So it wasn't as straightforward as working with the C library, and there were some difficulties there. But so our solution for this was to create a thin C wrapper around those C++ functions. In this way, our CHIUW could interoperate only with C and then still execute that C++ code tertiarily through the C code. And so the way that looked in practice was the C++ and the C code is compiled into an object file prior to compiling the CHIUW program. And then once you get to the level of compiling the CHIUW program, you'll link that object file with the CHIUW code, exposing that C API to the CHIUW code. And so once we were able to fit this C++ code in with our CHIUW code, we had much greater control over our Parquet API calls, just a library with much wider support, essentially. And we also had additional features that weren't supported in the C API, such as additional compression formats and a number of other features as well. And so just taking a step back and looking at what that kind of looked like in code, working with the C++ library. So here, starting at the highest level of the CHIUW code. So here, we're just calling the C function through our C interoperability. And so we have our extern procedure like you would have with any C interoperability. And that's just a C function that accepts a pointer to an array buffer. And so we can then pass our CHIUW array buffer to that C code through the C interoperability function. And that's how we can get that buffer down to C. And then once we're in the C code, at this level, all we're doing is really just passing along those parameters straight to our C++ code. So all that's going on at the C level is just calling the C++ code and passing along those parameters. So the entire function in this example, just for reading a Parquet column function, is just to return the result of calling the C++ function. And so from that level, once we get down to the C++ code, this is where we have access to the actual Parquet API, and this is where we can do the actual work and read into our CHIUW array buffer. And so this code on screen here isn't necessarily real code, but I think it demonstrates what's going on there, where we've essentially just opened our Parquet file, and now we're reading that file from, reading a column from that file directly into our CHIUW array. And so that's how we were able to work from CHIUW to C++ and get around that C++ interoperability issue that I mentioned. And so now to talk about some of the additional performance optimizations that went into this and some of the results as well. So starting with some performance here, this is this is the read performance of reading in 400 integer files, each of a 1/4 gigabyte size, so 100 gigabytes total on a Cray CS with InfiniBand HDR. And so similarly to the last graph, this is a performance graph, so higher is better. And so in the table here, you can see our initial C implementation that was about 500x worse. We've improved it with the initial C++ implementation on a single locale from about 0.003 gigabytes to 0.85 gigabytes. So about a 300x improvement there from our initial implementation. And we're only about 1.5x behind HDF5 with this initial implementation. And so we were actually already well within our goal range out of the box with this C++ implementation. You can see we're already exceeding that 2.5x goal that we'd set from ourselves with the C++ implementation. And yeah, so we saw some very promising results from switching to the C++ API. And so I would mention, though, that this switch to the C++ API was more than just essentially interchanging a single C API call with a single C++ API call. There was a lot of additional things that went into this, like using that metadata that we didn't have access to in C, and just taking advantage of a couple of other obvious things that we just didn't have access to in the C code. Yeah, so that's where our initial performance landed on this. And so once we had seen these results, we were pretty satisfied with the performance. Like I mentioned, we had already exceeded our goal 2.5x of HDF5, but we were still able to identify a couple of optimizations from there. And the first kind of two key optimizations that I'm pointing out is switching to a low level batching API from a standard API, just the regular API read file call, essentially provided by the Parquet API. And how I would describe this optimization is, so you can think of the standard API call was essentially just a Parquet stock function that says, read this column from this file. And what that meant is that we had to read directly into an arrow data structure. We couldn't read just into an arbitrary data buffer. And that kind of inhibited us from reading into our chapel array. And what that meant is we had to store this array. We had to have this array. We had to have our chapel array buffer as well as our arrow data structure storing the file at the same time. So we essentially had to store two copies of the file column at a time. So there's quite a bit of memory. Yeah, there was some poor use of the memory there, and we also just weren't reading directly into our we also had to do the copy into our chapel array, which was also costing us some more time. And what this low-level API allowed us to do is just read directly into a buffer, just large chunks of data at a time. So in that way, we were able to cut down that temporary copy. And the performance results in this were admittedly a little bit modest, but what did come out of this was a reduction of about half in memory usage, going from just having only the chapel array buffer to store the data. And then the second optimization, which resulted in much more significant performance improvements, was parallelizing our file reads to read multiple files concurrently. And what this looked like in actual implementation was as simple as changing a for loop to a for all loop, just utilizing chapel's parallel constructs there. And so that resulted in some very significant performance improvements that we'll see on the next slide. Yeah, so now looking at the performance improvements of those optimizations here, you'll see we're using the same benchmark here with 400 files of 1/4 gigabyte of integer elements, each on a tray CS with InfiniBand HDR, so 100 gigabytes total. And so first taking a look at the single locale before taking a look at the 16 locale performance. So you'll notice that our Parquet batch read, it jumped up about a 15% performance improvement, bringing us a little closer to HDF5. But then once we get to the parallel read, we actually see about a 12x performance improvement there. And now we're actually well outperforming HDF5's performance with Parquet. And it's similar on the 16 locale throughput, where we see significant performance improvements from the parallel reads, but a little bit more modest improvements from the batch read. And both are significantly performing HDF5. And so there's a couple of reasons for this, but I think the biggest one is that HDF5 is not actually a thread-safe library. So HDF5 can only read a single file at a time on each locale, whereas Parquet didn't have that same limitation. So in this case, where we're reading 16 locales, 400 files, what's essentially going on behind the scenes there is each locale is reading in 25 files concurrently. So each locale is reading in a bunch of files at the same time, and that can't be done in HDF5, where each process can only read a single file. And so because of that discrepancy between the parallelism allowed by Parquet and not in HDF5, we were actually able to kind of flip that goal around a little bit, where we were hoping to be within 2.5x of the HDF5 performance. We were actually able to get 2.5 times the HDF5 performance. So HDF5 was about 12 gigabytes per second, and Parquet was about 30 gigabytes per second for the read file case. So we were able to get to kind of invert that goal a little bit. Yeah, and so I would mention another reason for this is Parquet is designed specifically for data science, making it a natural fit with ARKOUDA. And like I showed on one of the initial slides, Parquet's columnar file format it fits really well with ARKOUDA. ARKOUDA actually only supports reading in single columns at a time from files. So Parquet was just a really natural fit with ARKOUDA. And I think that makes sense just because ARKOUDA is both a data science and an HPC library. So whereas HDF5 fits the HPC aspect of that, Parquet kind of fit the other gap there with the data science specialty. And so just to wrap up the talk and get into the conclusion here, we were able to interoperate with C++ and Chapel by using a thin C wrapper around our C++ functions and utilize Chapel C interoperability to call into C. And then also our single node read performance improved from 0.003 gigabytes per second in the initial C implementation to a little over 30 gigabytes per second. So we saw over 1,000x improvement there. And then we were also quite surprised to see that Parquet outperformed HDF5's read performance for our 16 locale benchmark by 2.5x. And the reason this was so surprising is because, like I mentioned, HDF5 is designed specifically for HPC. So you kind of would just assume that HDF5 would be a better fit here. But yeah, we saw that wasn't quite the case here due to the parallelism that I mentioned. And then the last thing I want to mention, just kind of a nod towards Chapel. So our largest performance gain here came from parallel features in Chapel. Just that simple change from a for loop to a for all loop, a 3-character change that resulted in about a 3x speed up. So we were able to take advantage of Chapel's concurrency things and then some of Chapel's concurrency features and then take credit for those. So that's just one of the great things about using Chapel is you get credit for performance optimizations without putting in much effort there. And yeah, so that concludes all I had for the talk. Thank you for listening. And are there any questions?